Today, we're diving into something called TurboQuant. It's a seriously cool new algorithm that's making our biggest, baddest AI models smaller and faster without, and this is the key part, without losing performance. So let's unpack how this thing works and what it could mean for, well, everything in AI.
It's no secret, right? AI models are getting monstrously big. And with that size comes a massive headache, a memory problem. We're creating a data traffic jam that's slowing everything down, and it's quickly becoming one of the biggest hurdles in AI development.
And really, this isn't just some small annoyance. This memory bottleneck is a hard wall that researchers are slamming into. It puts a very real ceiling on how big, how complex, and frankly, how smart our AI can get. So let's break it down. For a large language model to be good, it needs two things: a huge model size and a long context window. But both of those things demand an insane amount of memory. The real slowdown, what we call latency, comes from moving data between the big main memory, that's HBM, and the super-fast memory right on the chip, the SRAM. And the biggest memory hog in this whole process? It's something called the KV cache. Just think of it as the model's short-term memory. The more you talk to it, the bigger this cache gets, and it becomes this giant ball and chain that has to be dragged back and forth, slowing everything to a crawl.
So how do you solve a problem where your data is just too big? Well, engineers have a classic trick up their sleeve, an idea that's been around for ages. It's called quantization.
Vector quantization, or VQ for short, is basically just a super clever way to compress data. You take these long lists of really precise numbers, we call them high-dimensional vectors, and you squish them down into much simpler, smaller numbers. The whole game is to shrink the data as much as possible while losing as little information as you can. You want to keep the important stuff, the core meaning, while throwing away the unnecessary precision. And this is where TurboQuant walks onto the stage with a shockingly simple yet brilliant idea. It all boils down to one thing: a random spin. Okay, to really get why TurboQuant is such a big deal, you have to see it next to the old way of doing things. Standard methods, like product quantization, are, well, they're kind of clunky. They're data-dependent, which means you have to pre-train them on a ton of data just to get them to work. That's slow, and it's totally useless for data that's changing all the time. But TurboQuant? It's data oblivious. It doesn't need to see any data beforehand. It just works, on the fly, which makes it absolutely perfect for compressing that dynamic KV cache we were just talking about.
So how does it pull off this magic trick? It's an amazing four-step dance. 1. You take any vector. 2. You hit it with a random and very computationally cheap rotation. 3. This is the genius part. That random spin forces all the numbers in the vector to fall into a perfectly predictable pattern, a statistical shape called a beta distribution. And 4, because that pattern is now known, you can just slap a simple, pre-made, one-size-fits-all quantizer onto each coordinate. It literally turns chaos into predictable order and then compresses it.
Let's just sit with that for a second, because the beta distribution is the secret ingredient. It's this wild, counterintuitive fact about geometry in high dimensions. You could have a vector where the numbers are completely random, all over the place. But the moment you apply a random rotation, they all snap into place, all conforming to this one known statistical curve. It's kind of like shaking a snow globe, you know? The flakes start out as a total mess, but they always settle down into a predictable pile. That predictability is what lets TurboQuant be so fast and universal.
And you don't have to take my word for it. Here it is from the researchers themselves. They spell it out right here. You randomly rotate the vectors, which creates that predictable beta distribution, and then you use that to just apply a simple, optimal compressor to each number individually. It's elegant.
All right, that all sounds great in theory, but does it actually work in the real world? Let's look at the results. So the researchers made two versions. Look at the one on the left. See how the error is a perfect bell curve, centered right on 0? That means it's unbiased. It's just as likely to guess a little too high as it is a little too low. For things like similarity search, this is absolutely critical, because it means the small errors average out to 0 and don't skew your results. The version on the right is tuned for a different task, and you can see it has a clear bias. The takeaway is that this is a flexible tool.
Now this graph is everything. The blue and purple lines, that's TurboQuant's error rate. But that dashed green line, that's not another algorithm. That's the mathematical limit. It's called the Shannon lower bound, and it represents the absolute best any compression algorithm could ever possibly do, even in theory. And just look how tightly TurboQuant is hugging that line. It's not just great, it's pushing the very boundaries of what's mathematically possible.
And here is the real-world payoff. This is from the needle in a haystack test, where an AI has to find one specific piece of information inside a huge wall of text. The results here show a model using TurboQuant to compress its memory by 4 times, and it performs identically to the full-fat, uncompressed model. It finds the needle perfectly, every single time.
And the score just proves it. The original full-precision model got a score of 0.997, and the model using TurboQuant, with its memory slashed by 75%, also 0.997. Absolutely zero drop in performance. It's incredible.
So what does this all add up to? When you put it all together, you realize we're talking about something pretty revolutionary. We're talking about compression that's almost perfect for almost no cost.
This table really says it all. The old way was slow. TurboQuant is ridiculously fast. The old way needed lots of pre-training. TurboQuant works instantly, online. The old way was suboptimal. TurboQuant is verifiably near optimal. On every single metric that matters, it's not just an improvement, it's a complete game changer.
And for anyone who loves the math, here's the final nail in the coffin. The paper proves, mathematically, that TurboQuant's error is guaranteed to be within a factor of about 2.7 of that theoretical perfect limit we saw. It's provably one of the most efficient quantizers that can exist. And that leaves us with this final big question. We've just seen solid proof of 4x compression with literally zero performance loss, and there's a reason to believe we can push it even further. So what happens now? What becomes possible when our biggest models can be shrunk down this much with no downside? Does this mean truly powerful AI running locally on your phone? Does it mean AIs with memories that are 5-10 times longer than they are today? TurboQuant isn't just a solution to a problem. It's a key that unlocks a whole new set of doors.